Hello everyone, I hope you're all safe and sound. Welcome to the 10th lecture on analog and digital electronic circuits, in which we will study the Darlington configuration, which is also called the Darlington pair. So we will analyze the Darlington pair for its DC currents, and we will find its small signal parameters, including transconductance, small signal input resistance, and small signal output resistance. So the Darlington pair, as shown in this diagram, is actually direct coupling of two bipolar junction transistors, in which the emitter terminal of the first transistor is directly connected to the base terminal of the second transistor. So actually, it can be thought of as a multi-stage amplifier, but instead of full amplifier circuits, we cascade the transistors. It can also be thought of as a direct coupling of two common collector configurations. So if you remember, then for a common collector configuration, input is applied at the base and output is taken from the collector. So if this is the input terminal of the overall circuit, then you can think of this transistor as the first stage common collector amplifier, because the input is applied to the base, output is taken from the emitter, which is then applied to the base of the second transistor. So if you take the output from the emitter of the second stage, then this is another common collector amplifier. So either you can think of it as a direct coupling of two BJTs or two common collector amplifiers. But I hope that by simply looking at the circuit, you can analyze or surmise that this configuration of two cascaded transistors actually results in a very high current gain. So a simple qualitative analysis can, in fact, it shows that since the emitter current here is the amplified version of the base current, and since this emitter current is fed into the base terminal of the second transistor, then this final emitter current is a further amplified version of the input base current. So the emitter current is related to the base current through beta. This emitter current in turn is related to this emitter current through beta. So the final emitter current scales as beta square with the base current. So you can directly hopefully see that without doing any mathematical quantitative analysis, you can see that this Darlington pair configuration is a high current gain configuration. So in the analysis, in the DC as well as the AC analysis, I will assume different parameters for these two transistors. So I will call this transistor as the first transistor, and the transistor in the second stage as the second transistor. And I will assume different values for the current gain, saturation current, and early voltage for the two devices. However, since thermal voltage depends upon the temperature, charge of the electron, and Boltzmann's constant, it will be taken to be the same for the two devices, for the two transistors. So I've labeled the currents and voltages here. These are the total currents and voltages. But at DC, you can see that this total DC collector current is the sum of the two DC collector currents for the first and for this transistor and this transistor. Furthermore, this we know that this collector current is related to the base current through beta, and the emitter current, which is the base current of the second transistor, is related to the again to the collector current of the second transistor through beta. So we can write the exact expression for the total collector current by writing it down as the sum of the two collector currents. IC1 is beta 1 times IB. So I will call I, because IB is the total input current. I will write IB1 as IB, and I will write IE2 as IE, because IE is the total emitter current at the final output. So IC1 is beta 1 times IB1, which is IB. IC2 is beta 2 times IB2, and IB2 is IE1, which in turn is equal to beta plus 1 times IB. or IDE1. So taking IDE out common, uh, we can realize straight away that the ratio of the collector to base current is equal to this factor. So we know that for a transistor, the ratio of the collector to base current is called the beta of the transistor. So we can define this factor as the beta of the Darlington pair of the overall circuit. That is, the total collector current is related to the total base current through this factor, which we call as the beta of the overall circuit of the beta of the Darlington pair. We denote it by beta subscript DP. Similarly, emitter current, total emitter current, which is IE2, which I represent as IE. So total emitter current is the emitter current of the second transistor, and it is related to the base current of the second transistor through this relation. But base current of the second transistor is the emitter current of the first transistor, which is related to the base current of the first transistor through this factor, beta plus 1. So again, I can multiply and open up all the terms, and realizing that we have already called this term as beta dp. So replacing this with beta dp, we get this expression. And you can see that this again is consistent with the relation of the emitter current with the base current of a single transistor. So this expression here is consistent with the expression of the collector current relating to, which relates the collector current with the base current of a single transistor. And this expression here is consistent with the equation of the emitter current, which is related to the base current through this expression. So beta dp times id is ic. So if you open it up, then again we get the usual current equation that the emitter current is equal to the sum of the collector current and base current. So from these equations, you can see that this equation relates the collector current to the base current through the beta of the circuit. This equation relates the emitter current to the base current through beta plus 1, where beta is the current gain of the overall circuit. And then we get a transistor-like equation here as well, that the emitter current is equal to the collector plus base current. So these three expressions, they allow us to replace this Darlington pair circuit with a single transistor model, which is also called the compound BJT. So this BJT, it represents these two, the direct coupling of these two transistors. So again, this is enabled by these equations that we get relations for the collector current and the emitter current in terms of the base current, which are given by the equations that relate the collector and emitter current to the base current for a transistor. So this is a transistor equation which relates the collector current to the base current. This is a transistor equation. By transistor equation, I mean equation that we get for the currents for a transistor, which relates emitter current to the base current. The only difference is that we have a different beta now. So we replace this device with this compound BJT single transistor model. So please note that while these two devices having beta 1 and beta 2, they are physical devices. This here is not a physical device. This is just a model that characterizes the terminal currents of this circuit. So this is just a single transistor compound BJT model of this circuit, whose beta is given by beta dp, which is equal to this factor. And you can see that because typically beta is large, so if beta is of the order of hundreds, then which typically it is, then this product here is much greater than the sum of these two beta. So this product scales as beta squared. So if beta 1 is equal to beta 2 is equal to beta, then we'll get this equation, this factor becomes beta squared plus 2 beta, which scales as beta squared. So the current gain, like I said before, when we very crudely, qualitatively analyze the circuit, that this Darlington pair is a high current device whose current gain scales as beta squared. So if beta is of the order of 100, then the current gain of the Darlington pair is of the order of 10,000 or so. So before we move on to finding the small signal parameters of the Darlington pair, uh, I would like to go through the small signal modeling of the transistor. We have already, using the small signal approximation, derived the model. So this is a quick review of those of the mathematical framework we use to derive the model. So ignoring the early effect, we know that the collector current of a transistor is related to the base emitter voltage through this exponential relation. So this is the collector current for the first transistor. This is the collector current for the second transistor, in which I can replace this overall voltage with DC plus AC voltage, and I can couple the DC exponential term with the saturation current, and I can call it the DC collector current. Uh, and then, as before, I think we did it in lecture 5. So as we did there, we can expand this exponential function through Taylor series around 0, and then using the small signal approximation, we can ignore all the higher order terms, which gives us this approximate linear expression for the collector current in terms of the base emitter voltage. And then we call this, because this is the DC, this is the contribution due to the DC voltage, so we call it the DC value of the collector current. And we call the second term, because this is the contribution due to the small signal base emitter voltage, we call this second term as the small signal collector current. Uh, and we define this ratio here as the transconductance of the transistor. So IC1 is equal to this thing, and we define GM1 as IC1 over VDE1, which gives us this ratio here. And similarly for the second transistor as well. We know that the base current is 1 over beta times the collector current. So we divide the two collector currents with the respective beta values, and we designate this, the first term in the two equations, as the DC content of the base current, and the second term as the small signal component of the base current, in which we write IC1 over VT as GM1 and IC2 over VT as GM2. And then we write the emitter current as IC over alpha. So IE1 is IC1 over alpha, IE2 is IC2 over alpha, and then putting in the value of IC1 and replacing DC IC1 over VT as GM1 and DC IC2 over VT as GM2. We find these relations where this is the contribution due to the DC voltage, so we call it the DC component of the emitter current, and this is the contribution due to the small signal component of the input voltage. We call it the small signal component of the emitter current. So, and then we define alpha like we did before. It's a beta over beta plus 1. So these formulations, they resulted in the small signal hybrid pi and T models for the transistors. So making use of the small signal hybrid pi model, I can draw the small signal AC equivalent circuit of the Darlington pair like this, in which the first transistor is represented by this hybrid pi model, and the second transistor is represented by this hybrid pi model. So the collector of the two transistors, they are connected. So the total collector is then divided into 2, and the emitter terminal of the first transistor is connected to the base terminal of the second transistor. So the emitter current is equal to the base current. The emitter current of the second transistor is the total emitter current, and the base current of the first transistor is the overall base current. So R pi 1 is the small signal resistance between base and emitter of the first transistor looking into the base, which is given by V pi 1 over ID1. V pi is the voltage across R pi 1. V pi is actually VBE. So VBE over IB. since this term is equal to IB, VBE over IB is equal to beta over GM. So R VBE over IB is defined as R5 and it is beta over GM. Similarly, since small signal emitter current is equal to this factor, so VBE over IE is equal to alpha over GM. So we define VBE over IE as small RE and it becomes alpha over GM. We use small RE, which is the resistance between base and emitter looking into the emitter. We make use of small RE when we use the T model for the device. And like I said, V pi is just VBE. Conventionally, we write the base the resistance looking into the base between base and emitter as R pi. So we write the corresponding voltage as V pi. So this is V pi 1. The voltage across R pi 2 is V pi 2, and the total voltage is V pi, which is the sum of V pi 1 and V pi 2. And we know we can from these equations we can see that GM VBE is beta IB. So this thing is equal to IB, so GM VBE is beta IB. So we can either write it as JM1 V pi 1 or beta 1 IB1, or as G, and similarly here as GM2 V pi 2 or beta 2 IB2, one and the same. We designate the output collector emitter voltage as small VCE. So this is the small signal AC equivalent circuit of the Darlington pair. We can further find the relations between the small signal parameters of these two transistors. So since GM is given by IC or VT, so for the second transistor it is given by the DC current of the second transistor, DC collector current of the second transistor divided by VT. So IC2 is equal to beta 2 times IB2, and IB2 is IE1, because the base current for the second transistor is the emitter current of the first transistor. The two are directly connected. The base and terminal of the second transistor is directly connected to the emitter terminal of the first transistor. So IB2 is IE1, and IE1 in turn is IC1 over alpha 1. So IC1 over VT is then GM1. So GM2 is related to GM1 through this factor. Similarly, R pi 2 is VT over IB2 because R pi is V pi over IB. So R pi is beta over GM. So GM is IC over VT. So VT goes into the numerator, beta when it comes into the denominator, it becomes IC over beta. So R pi becomes VT over IB. So R pi 2 is VT over IB2, the base current of the second transistor, which is equal to the emitter current of the first transistor, which in turn is related to the base current of the first transistor through this expression. So VT over IB1 is R pi 1. So this relates R pi 2 with R pi 1 through this factor of 1 over beta 1 plus 1. And RE2 similarly is VT over IE, because again, GM is IC over VT, so VT goes into the numerator. Alpha, when it comes into the denominator, makes the denominator IC over alpha, which is IE. So small re is VT over IE. So for the second transistor, it is VT over IE2. IE2 is related to the base current of the second transistor through this expression. The base current of the second transistor is the emitter current of the first transistor. So IE2 is beta 2 plus 1 times IE1, and IE1 is related to the base current of the first transistor through beta plus 1 plus 1. So VT over IB1 is R pi 1, and R pi 1 over beta 1 plus 1 from the resistance reflection rule is RE1. So small RE2 is related to small RE1 through this factor of 1 over beta 2 plus 1. Now, using these relations and this a small signal AC equivalent circuit of the Darlington pair, we can find the small signal parameters of the Darlington pair. So we'll start with the transconductance, which we define as before for a single transistor. The transconductance is defined as the ratio of the small signal collector current to small signal base emitter voltage. So for the Darlington pair, we define the transconductance as the small signal collector current, total collector current, to the small signal total base emitter voltage of the Darlington pair. So it is small IC over VBE. VBE is V pi, So small IC is the sum of the collector currents for the two transistors, which in turn are given by GM1 V pi 1 and GM2 V pi 2, because these two currents are GM1 V pi 1 and GM2 V pi 2. V pi 1 in turn is given by the base current of the first transistor times R pi 1. Base current of the first transistor is the total input current, so I write it as IB. Whereas V pi 2 is given by the base current of the second transistor times R pi 2, and base current of the second transistor is equal to the emitter current of the first transistor. So the base current of the first transistor is IB, so IB times R pi 1 is V pi 1. And then IB2 times R pi 2 is V pi 2, but IB2 is equal to IE1, which is the sum of these two currents, IB1 and beta 1 IB1. So IE1 is given by beta 1 plus 1 times IB. So IE1 is given as beta 1 plus 1 times IB. So since V pi is the sum of these two voltages, V pi 1 and V pi 2, I add these two terms, take IB out common, and this is the relation I get. Then in this expression, I replace IB as V pi over this term. So V pi 1 becomes V pi over this term times R pi 1. And then using this relation, which gives us R pi 1 as beta 1 plus 1 times R pi 2. So beta 1 plus 1 times R pi 2 is R pi 1. So we get R pi 1 over 2 R pi 1, which is 1 by 2. So V pi 1 becomes V pi by 2. And since V pi is the sum of V pi 1 and V pi 2, V pi 2 is also V pi by 2. So like I said, I've used this equation to obtain this result. Therefore, we can put these values back here. So V pi 1 is V pi by 2, V pi 2 is V pi by 2. So GMDP becomes the arithmetic mean of GM1 and GM2. So I take GM1 by 2 out as common, and I use 13 to replace GM2 with GM1. So I replace GM2 with this factor here. So GM2 is beta 2 over alpha 1 times GM1. So I take GM1 by 2 out common, and I'm left with 1 plus beta 2 over alpha 1, which when solved gives me this relation between the overall transconductance and GM1. And then again, using this expression in 13, I can replace GM1 with alpha 1 over beta 2 times GM2. So alpha 1 will get cancelled out, and I'll have a beta 2 in the denominator. So this relation, this expression relates GM dt in terms of GM2. So the transconductance of the overall Darlington pair can be given in terms of GM1 or GM2. These two expressions are equal to each other. Small signal resistance looking into the base terminal of the Darlington pair is again denoted by R, because we denote such a small signal resistance as R pi. So for the Darlington pair, I add this subscript dp. So R pi dp is defined as we define it for a transistor. That is, it is the ratio of the base emitter voltage to the base current. So the total base emitter voltage for the Darlington pair is the sum of these two, V pi 1 and V pi 2. V pi 1 over IB by definition is R pi 1. V pi 2 is the base current of the second transistor, which is the emitter current of the first transistor, times R pi 2. And IE1 is beta 1 plus 1 times IB. So IB gets cancelled out, and this is the relation we get. So again, using 14, we can see that this term here is equal to R pi 1. So we can express R pi dp as 2 R pi 1. Or since R pi 1 is equal to this term, we can express it as equivalently as 2 times beta 1 plus 1 R pi 2. So this is the small signal resistance between the base and emitter looking into the base for the Darlington pair. Similarly, small signal resistance between base and emitter looking into the emitter terminal is represented by R small re with an additional subscript of dp. And we define it as we define it for the transistor as the ratio of base to emitter voltage to the emitter current. So VBE is just another name for V pi. So VBE is equal to VBE1 plus VBE2. VBE1 is IB1 R pi 1. VBE2 is IE1 R pi 2. So uh, IB1 R pi 1 is VBE1, IE1 R pi 2 is VBE2. IB or IB1 is equal to IE1 over beta 1 plus 1. And IE, which is the emitter current of the second transistor, is beta 2 plus 1 times IB2, which is equal to IE1. So I can cancel IE1, and this is what I'll be left with. So beta 1 plus 1, R pi 1 over beta 1 plus 1 is small re1. So I get small re of the Darlington pair as the sum of small re1 divided by beta 2 plus 1 plus small re2, which again, from the expression in 15, we know that small re2 is equal to small re1 divided by beta 2 plus 1. So I can represent small re of the Darlington pair in terms of small re1 like this. And since small re1 over beta 2 plus 1 is equal to small re2, so I can equivalently represent it as 2 times small re2. So using these relations, we can show that GM of the Darlington pair times V pi is equal to small ic, which is equal to small ic1 plus small ic2, which is equal to beta 1 times IB, and this is equal to beta 2 times IB2, which is IE1. And IE1 is beta 1 plus 1 times IB. So I can take IB out as common, and this, the remaining factor, which is beta 1 plus beta 2 plus beta 1 times beta 2, is the beta of the Darlington pair. So we can equivalently represent GM V pi as beta IB as before for a transistor. Just like as we did for a transistor, we can write for the Darlington pair the GM dP times V pi as beta dP times IB. Alternately, we can write GM dP times VBE, because VBE is the same as V pi, again as the total collector current, which is the sum of the two collector currents. Now, instead of representing these collector currents in terms of base current, we can represent these collector currents in terms of the corresponding emitter currents. So IC1 is alpha 1 times IE1, IC2 is alpha 2 times IE2. IE1 is related to IE, because IE1 is the base current of the second transistor, so it is related to IE2 through this factor. And alpha 1 is beta 1 over beta 1 plus 1. So I can take IE2 out as common. IE2 is the total emitter current at the output, which is IE. So I can simplify this term in the parentheses. So this is beta dP, and this is beta dP plus 1, which is alpha dP. So equivalently, I can represent this term GM dP times VBE as alpha dP times IE. Moreover, I can represent the total emitter current, which is IE2, in terms of the base current of the second transistor through this relation. Since the base current of second transistor is IE1, I can represent IE1 in terms of the total input current IB through beta 1 plus 1. So I can open this factor up, and this term is beta dP. So beta dP IB plus IB is IC plus IB, because IC is beta dP times IB. So I can represent small signal emitter current as the sum of small signal collector current and the small signal base current. So using these relations and the models, the small signal parameters we just derived, this R pi and GM, we can express the small signal AC equivalent circuit through these small signal models for the Darlington pair. So R pi dt was defined as Vp over Ib. So, sorry, V pi over Ib. So V pi is Ib times R pi dt. IC is uh, Gm dt V pi, which is also equal to beta dt Id. So it is given by this voltage controlled or current controlled current source. Vp is the voltage between collector and emitter, and the sum of these two currents is equal to IE, as shown here. Similarly, we can represent IC, which is equal to GMdP times VBE. So IC is GMdP times VBE in terms of IE through this relation. So IC can be represented in terms of VBE or IE as a voltage controlled or a current controlled current source. Our PDP was defined as VBE over small IE. So we can represent the forward bias base emitter junction through this small signal resistance, REDP, and the sum of base current and collector current as before is equal to the emitter current. So the small signal parameters we just derived, they result in these two small signal models for the Darlington pair. And you could see it coming because we were already able to replace the Darlington pair with a single transistor. So uh, you could think at that point as well that so let me go back to the circuit equivalent model. So yeah, so you could already think here that since we are able to represent this device as a single transistor, then the small signal model of this circuit will resemble the small signal model of a transistor, because it just the Darlington pair just acts as a compound BJT with a high current gain. So ignoring the early effect, we get a similar model for the Darlington pair, a model which is exactly similar to that of a transistor. The only difference is that the small signal parameters R pi, GM, small RE, they are obviously different and are represented in terms of the small signal parameters of the two transistors. So if we look at the resistance, because we have ignored the early effect, then if we look at the resistance between collector and emitter, looking into the collector, then from these two models you can see that that resistance is infinity, because no matter what the voltage between collector and emitter is, the collector current is independent of that voltage. So the collector current is independent of the voltage between collector and emitter, which means that changing the collector emitter voltage will not change the collector current. This indicates that the resistance between collector and emitter looking into the collector is infinity. So from these models, the small r naught is infinity, which we typically we denote the small signal resistance looking into the collector between collector and emitter for transistor as small r naught. So here it is infinity because we have ignored the early effect. We have ignored small r naught 1 and small r naught 2 for the two transistors. So if we take into account the early effect for the two transistors, then the small signal AC equivalent circuit for the Darlington pair is augmented by these two resistors of small r naught 1 and small r naught 2. Everything else remains the same. IE1 obviously is now beta 1 IB1 plus IB1 plus the current through small r naught 1. So we should use this circuit to find the resistance seen looking into the collector between collector and emitter, because now the resistance will be finite. And since we can represent this overall circuit as a current amplifier, that is the output current. So if we think of this overall circuit as a two-port network, where the base and emitter, they form the input port, and collector and emitter, they form the output port, then the input current is IB and the output current is minus IC. So minus IC is definitely an amplified version of IB. So we can think of it as a current amplifier. And we've already modeled the current amplifier in one of the previous lectures. So we've already derived a two-port model for the current amplifier using H parameters. So there we were able to find out the output resistance, the resistance mean looking into the output of the current amplifier um, in terms of one of the H parameters, and it was defined uh, by open circuiting the input. So the output resistance there was defined uh, by open circuiting the input. So if we, so unlike a voltage amplifier where we short circuit the input to find the output resistance, the output resistance of a current amplifier is defined at open circuited input. So if we open circuit the input, then base current IB becomes zero, which gives V pi 1 to be zero because there is no current through R pi 1. So V pi 1 becomes zero. GM1 V pi 1 becomes zero. This current becomes zero. So this branch becomes open circuit. So this branch is also open circuit because there is no path for the current to flow. So this circuit, this bit of the circuit is essentially out of the circuit. So we are left with R01 in series with R pi 2, and then this source connected here in parallel with R02. So this is the simplified AC equivalent circuit of the Darlington pair for finding the output resistance, the resistance between collector and emitter. So what we do is we connect a voltage source here, and we open circuit the input, and then we take the ratio of the voltage of the source to the current drawn through the source by the circuit. That ratio is equal to the resistance between collector and emitter looking into the collector. So when we open circuit the input, that this is what we get. This is the simplified circuit. I just explained that this bit is essentially out of the circuit. So R01 is in series with R pi 2. So a Vs over Is will be the output resistance between collector and emitter looking into the collector. So we denote it by a small R0 subscript dp. So from this circuit, you can see that Is divides between this branch, and this branch. So small R0 dp is Vs over Is. So, and Is is the current through this branch, which is Vs over R02 plus beta 2 times IB2 plus this current, which is Vs2, which is Vs divided by the sum of these two resistors. So Vs IB2 in turn, this IB2, which is the current through R pi 2 and hence R01. This is given by this factor. So IB2 is Vs over. So IB2 is the current through this branch. So and the current through this branch is Vs over R01 plus R pi 2. So I can replace IB2 with this term, Vs over R01 plus R pi 2. And then I can take Vs out common and cancel with the Vs in the numerator. And I can combine these two terms. So this becomes beta 2 plus 1 over this denominator. They have common denominator. So this is the denominator. And then I can write this expression like this, in which I can simplify and take the inverse to get this form for the output resistance of the Darlington pair between collector and emitter looking into the collector. So if we assume, so far we have assumed that the parameters of the two devices are different, but if for simplicity we assume that the early voltage of the two transistors, they are the same, which is not a bad assumption because a Darlington pair typically comes as a package, so the two transistors, they come through the same manufacturing process. So this is a reasonable assumption. So if we assume that the early voltage for the two transistors is the same, represented as VA, then we can relate the output resistance of the second transistor to the output resistance of the first transistor, just like we related R pi and RE. So we can relate small R02 with small R01 through this relation. So small R0 is given by VA over IC. So small R02 is VA over IC2. IC2 is beta 2 times IB2. IB2 is IE1. And in turn, IE1 is IC1 over alpha 1. So VA over IC1 is small R01. So R02 is alpha 1 over beta 2 times small R01. So furthermore, on top of this assumption, if we further assume that uh, the beta values for the two transistors, they are very large. That is, we assume that beta 2 plus 1 is approximately beta 2, which gives alpha 2 to be 1. And then we further we assume that alpha 1 is also approximately 1. Then I can simplify this term. So this term becomes, so beta 2 plus 1 is approximately beta 2. R naught 1 is VA over IC1. So I can take the beta in the numerator and divide the denominator with it. R pi 2 is beta, R pi 2 is VT over IB2, and then this beta from the numerator. IC1 is alpha times IE1, alpha 1 times IE1. So alpha 1 is approximately 1. So VA over beta 2 IC1 is VA over beta 2 IE1. And beta 2 IB2 is IC2. And then since IE1 is IB2, so beta 2 IB2 is IC2. So the first term is VA over IC2, second term is VT over IC2. VA is much, much larger than VT typically. So this sum is approximately equal to VA over IC2. So VA over IC2 is small r naught 2. So we get 2 over small r naught 2, the inverse of which is small r naught 2 divided by 2. So we can approximate the small signal output resistance of Darlington pair and represent it in terms of small r naught 2 like this. Or we can use this relation in which we can assume, we've already assumed alpha to be 1, alpha 1 to be 1. Then we can replace our small r naught 2 with small r naught 1 divided by beta 2. So the output resistance r naught dp is either small r naught 2 by 2 or small r naught 1 divided by 2 times beta 2. So this is an approximate uh, expression for the output resistance of the Darlington pair using some very reasonable assumptions. So with this information, we can augment the small signal model for the Darlington pair we derived earlier with this resistor here. So by definition, this is the resistance seen looking into the collector, this port made up of collector and emitter at open circuited input. So when you open circuit input, ID becomes 0, this current becomes 0, and all we are left with is this small signal resistance. So the placement of this resistance here is justified and consistent. Similarly, for the T model, we can place this resistance between collector and emitter like this. So again, this is the resistance seen looking between collector and emitter, looking into the collector at open circuited input. So if we assume that the input port is made up of base emitter, output port is made up of collector base, then open circuiting the input will result in zero result in 0 IB. Sorry. So when I open circuit the input, IB becomes 0, which means that since this is equal to beta times IB, so this current becomes 0. So this becomes open circuit. This current is 0, so there is no voltage here. This is essentially out of the circuit as well. So the resistance between collector and emitter is just small r naught, which is again justified. The placement of which is again justified and is consistent. So these are the augmented models for the small signal models for the Darlington pair when we take into account the effect of the early effect for the two transistors. But please note that these are approximate models because in these models the small signal parameters GM, R pi, and small re, they have been computed ignoring the early effect, and only small r naught has been computed by taking into account the early effect. All the other parameters, they were computed ignoring the early effect. So this is an approximate small signal augmented model for the Darlington pair. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.